All right, hello everyone. So for this video, I'm going to go over the first of our free response questions that I posted. I'll do another video with the second question, but this first one, well, they both are about electrostatics and electric potential. I'm going to give a super short review of the important stuff for this problem, but keep in mind that these two units would make up about 25% of your test, so I won't be able to go through the entire background of it in this one video, but for our purposes, a couple of important things. One is that if you have a positive test charge, you have electric field lines emanating out from it. And if you have a negative test charge, you have the electric field lines going towards it. Okay. Now keep in mind, I know it's hard to see when this is a little whiteboard in a video like this. So anytime I write something out, I'll try to be as careful as I can about what each symbol means in case you can't read it. So therefore, the important thing here is the positive charge is electric field lines emanating out from it. Negative has it going towards it. And I'll also remind you about the equations. Because they're going to ask for electric field and electric potential, we'll just start with electric field. Represent that with the letter or the symbol E. And that's equal to the force per unit charge. And if we simplify this just a little bit, we get K Q over R squared. That would be our formula for electric field. And the units for it are joules per coulomb. I'm sorry, newtons per coulomb. Joules per coulomb is actually the unit for electric potential. And so electric potential is represented with the symbol V, letter V. And that's equal to the work per unit charge. And you can simplify this down to K Q over R. Now, if you look at these two equations, force per unit charge, work per unit charge, they look really similar. In fact, they are very similar, but there are important differences and subtle differences. Think of the electric field. Well, first, the electric field is a vector quantity, meaning it has a magnitude and a direction associated with it. The electric potential only has a magnitude associated with it, meaning just a number. So if you found the electric field, not only are you finding the value of the field, you're also finding which way it points. Whereas the electric potential is just some value. And if you want to relate those two, if you say, well, what exactly is the difference? And like I said, it's subtle, but the basic difference is that the electric field tells you how the electric potential changes when you move from one spot to another. So think of it like this. Think of the potential representing, say, the steepness of a hill. And think of the electric field as representing the steepness, but also how that steepness is changing if you were to move around that hill. Right? So maybe you go up the hill. The electric field will tell you how the potential changes as you go up the hill, or maybe you go down or whatever direction you're going. But the electric field represents the change in potential. So important differences. And the units for this are joules per coulomb. Joules because work is measured in joules, charge again is measured in coulombs. So that's the super short overview. I recommend Khan Academy if you have questions on the basics of it. Look over the notes that we did first semester. Ask me questions if you need more help. But so for this problem, we have four charges that are oriented in this square right here. We have a positive, a negative, and a positive that are oriented like this. And then we're asked about the electric potential and the electric field in the middle of the square. It also tells us that each side of the square is a length S. So therefore, just so we put this in here, the radius in that equation that I just had up on the board, for both potential and electric field, we had a radius in there. What does that radius represent? The radius represents the distance from that point to the charge. And so you can see that if we're right in the center of a square, you have the same radius going to each charge, the same distance to each charge. Now AP, when they give you electrostatics problems, it's always going to make, almost always going to make use of some sort of symmetry. In this case, we have a couple of symmetries. One symmetry is that it's aligned or configured in a square like this. Another symmetry that we have are that we have equal numbers of positive and negative charges. So both those things can sort of simplify the problem because there's a symmetry related there. Okay, well, if this is a distance R and this total here, this total side is a distance S, I hope it's clear that we can write each side of this triangle that's inside of the square as a distance of s over 2. This is s over 2. This distance right here is s over 2. And so the first part of the question wants to know, what is the electric potential at the center? Now, electric potential is a scalar, meaning it's a number, it's a magnitude. It doesn't depend on direction. Because it doesn't depend on direction, it doesn't depend on how these charges are oriented. So if I were to take this negative and swap it with this positive, or take this negative and swap it with this positive over here, it doesn't matter. The total amount is still going to be the same, because the distance between these charges, this distance r, this radius, doesn't change. The orientation might change, but the distance between them does not. So therefore, if we have 2 positives and 2 negatives, and our total potential is just adding all those up, our total potential then, for part A, our total potential is V is equal to 0. 2 positives cancel with 2 negatives, potential of 0. All right, well then the electric field, now the electric field is a little more complicated because it does depend on the distance, I'm sorry, the direction. However, if we draw in our electric field lines, maybe we can see if the symmetry will help us a little bit. So I'm going to draw a dot to represent the center of the square. I am going to say that, well, again, I'm going to use the convention that electric field lines point out from positive charge and point towards a negative charge. So therefore, if I were to look at this negative charge up here in the corner, I would say the electric field lines will point towards it, like that. If I were to look at this positive electric field down here, or I'm sorry, positive electric charge down here, the field lines are going to emanate away from it. And the way we draw that in for the bottom right corner is we actually draw it over here. And then the same is true of this negative one down here. It's going to point towards it. And the same is true of this positive one over here, will point away from it. Therefore, because all these charges are equal in magnitude, but the only thing that's changing is their signs, they're equal in magnitude, and we have this symmetry here, we can say that the electric field then is 0. So that's good. Symmetry helps. All right, for part B. Part B, what they do now is they swap signs. So this positive, or I'm sorry, this negative charge becomes a positive, and this positive charge becomes a negative. And so, again, the distance between the center of the square and the charges doesn't change. The orientation did, but the distance does not. Therefore, for part B, our potential is still 0. However, our electric field is a little bit different now. So if I were to do the same thing I did for part A, which is to draw in the electric field lines, I would say, okay, well, the electric field lines are going to point towards negative Q. That didn't change. It's going to point towards negative Q down here. That didn't change. But take a look at this charge and this charge. Well, if you think about it, this charge now has electric field lines pointing away from it. And therefore, you're going to have another electric field line representing that bottom left corner pointing in the same direction as the negative charge up here. They add together, they reinforce each other. And one way to sort of think about this in terms that you're more familiar with is that two like charges repel each other, 2 opposite charges attract each other. Likes repel, opposites attract. And so therefore, if you were right in the center of the circle, you would say, okay, this positive charge is going to push me this way, and this negative charge is going to pull me this way. So they reinforce, they add together. And then the same is true of this other part right here. So they add together. Now, because it's a vector quantity, we need to know what the x and the y components are. The y component is going to point this way for these top 2, and the y component is going to point this way for these bottom 2. They're equal in magnitude, opposite in direction, and therefore these y components both cancel out. But the x components don't. The x component will point this way for these 2. It'll point in the same direction for these 2. Now notice, they're both pointing in this direction. They're both of equal magnitude. And so therefore, if I can find the x component of one of these charges, I can say the total x component is just adding the other 3 in there, adding them all together. So therefore, what I'm going to do is I'm going to find the x component of one charge, and then just multiply that by 4 to represent all 4 charges. So we have one charge right here with the hypotenuse pointing this way. This would be the electric field, the actual electric field. This would be the X component of the electric field. And this would be the Y component, which we already said is 0. Okay, well, the electric field, we already said, is equal to KQ over R squared. KQ over R squared. And to find the X component, this part right here, which is what we're interested in, we just multiply that by cosine of 45. This is a 45, 45, 90 triangle. Cosine of 45 is equal to the square root of 2 over 2. So therefore, put an X right here. Therefore, our field can also be written as KQ over R squared times the square root of 2 over 2. And again, because there's that symmetry, we can say that the total electric field then is just 4 times this amount. If this is what one of them is, then 4 of them is just 4 times this amount. So therefore, my answer is going to be E, the electric field, is equal to EX, because we have no electric field in the Y direction. And that's equal to 4 times K times Q times R squared times square root of 2 over 2. Now I will say this, is that AP likes the problem to be simplified and put in terms of the givens. What are the givens? Well, the givens aren't the radius right here. They don't write radius anywhere in this problem, but what they do write is S, representing the distance of one of the, or the lengths of one of the sides of that square. And so we can rewrite this radius in terms of this distance S. Because I said that one side of this triangle on the inside of this square is S over 2, I hope it's clear by using Pythagorean theorem that we can also write that R squared is equal to S squared over 2. I hope that's clear how I came up with that there. Therefore, I can replace this R squared with S squared over 2 in this equation and then do a little bit of simplifying. I'll leave that up to you, but what AP will want is for you to plug in this R squared here and then simplify everything down, but I'll leave that up to you guys. Other than that, we can also say, I don't believe it asks, but I believe we can also say that based on this symmetry here, the electric field, I don't think it asks, but we can say that the electric field is going to point directly to the right. There's no angle to it, it just points directly to the right. If this one points this way, this one points this way, the angles between the horizontal and these two vectors are the same, we know that the electric field is going to point directly to the right. So the answer then is just plugging in this and then stating the direction. And that's all there is.